Hi, welcome to another mini lecture on algebraic topology. We were talking about covering spaces, and now we are going to introduce a special kind of covering space, namely a universal covering space. A universal covering space is defined simply to be a covering space that is simply connected. Remember, that means that the covering space is path connected. Between every 2 points you can find a path, and the fundamental group of the covering space is trivial, or another way to say is the path between every 2 points is unique up to homotopy. You can deform every 2 paths into one another. So there is a condition for the existence of a universal covering space for a locally path-connected space X. And this is what we're going to look at here. So this is a lemma which says that let X be a locally path-connected space. If X has a universal covering, which I have just told you what it is, X must be semi-locally simply connected. So what does semi-locally simply connected mean? This is this definition here in the box. So the covering space is called semi-locally simply connected. If the following is true: for every X, so for every point X in X, we have that there exists an open subset U which contains X and which is path connected, and such that this condition here is true. So the map from the fundamental group Ux to the fundamental group pi1 of XX is trivial. So this is the map induced by the inclusion, which is a map of pointed spaces because it maps X to X. And so this is this definition, and we are going to prove this lemma. I've sketched the lemma here, the proof already, so I'm going to talk you through it. So this is our space X. Here we have a point X. We have an open subset containing X, and we have a covering space, which is again called E. So we can look at the pre-image of this open set, which we picture as a stack of disks, so disjoint disks, each of which is homomorphic to U. So another way to say it is that the pre-image is topologically equivalent to U cross the pre-image of X. And since we're assuming that X is locally path connected, we can as well assume that this U is also path connected, shrinking it a little bit if necessary. So U is path connected, and now let's look at a path component of the pre-image of U, and let's call this path component V. So V sits up here, and under this topological equivalence of the pre-image of U with U cross the pre-image of X, we have that this path component V is of this type. It is a subspace of this space, which looks like U cross Y, where Y is an element of the pre-image of X. And this means that if we look at a map Q, which is defined to be just the map P, just a projection map P restricted to V, then this is a topological equivalence of V with U. So my U looks exactly like my V, I guess. So this is U and up here is V. So we have this topological equivalence, and yeah, let's draw. Let's look at this diagram now. So we have these maps. So we have the inclusion of V point comma Y in E comma Y, which is again a map of pointed spaces. We have this topological equivalence of V and U, which we have just talked about. We have this projection of E cross Y to X cross X, and yeah, we have this inclusion of U cross X in X cross X, and now if we apply the functor pi1 to this, we get this commutative diagram of fundamental groups, and what we already know is that this one here is trivial. So the fundamental group pi1e comma y is trivial, because we have assumed that we have universal covering, and as I have mentioned, if the space is a universal covering, it means that it is simply connected, and the fundamental group is trivial. So this fundamental group is trivial, and this, so the homomorphism induced by Q is an isomorphism, because Q is an isomorphism, and by functoriality, isomorphisms here in the category of pointed spaces get mapped to an isomorphism of groups. And so if we go this way around this commutative diagram, we come across this trivial group. So this way, first here and then here, has to be a trivial map. So the other way has also to be the trivial map, but this is an isomorphism. So the only way to make this diagram commute is that this map is trivial, and this is the condition for semi-locally simply connected, and thus we have proved the lemma. Thank you for watching. See you soon.